Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 4.4.6. So, as promised, we're going to take a look at this picture and think of it as three cubics that are intersecting each other. You take three lines, that's equivalent to a cubic, and that was discussed in the last video. Okay, a cubic of sorts, that is, if you think of a cubic kind of polynomial in x and y up to degree 3. Okay, so let's look at this computation, a plus b plus c. So we first do a plus b, then we do c. So what kind of points do we have when we do that? We have a, b, and then we have, so this is actually a plus b is not the third point on the line, but the vertical partner of it's actually on that line. So we take a, b, and negative a plus b. That's actually on one line. That's the first line that we used for this addition process. Then on the next line, we have, so next we took its vertical partner, a plus b, and then we connected that with c, and we didn't get the sum. Instead, we got the point right before the sum, which is the vertical partner, see the negative, before we actually find that. So these are actually, so this is like the points on one of the lines and on the other one. Let's take a look at what that is. So this is like these points right here, and then these points right here on the red lines. So on this one red line and that one red line, and really this vertical line right here actually encompasses or includes those points. So really we get all the points that are on all the red lines, and that's what we get right there. Okay, now for this we do something very similar. So B and C, and the third intersection point on that, then we drop down through the vertical line to the next point. So in the blue we have all of that. Okay, those first three are just the three intersections on the blue, and then we drop down here, and then we go from there and the common end, and that's actually what we get. Okay, that's what these are right here. Okay, so we have a list of the list of points that we get from intersecting, from the blue intersecting the elliptic curve and the red intersecting the elliptic curve. Okay, now this little description just mentions that all of the cubics that we're going to deal with, we're going to say that they actually have a point at it. They actually intersect at the point of infinity as well. So we're always going to include the point of infinity in there. Now this can be generalized and beefed up to 3 dimensions as well, and to see that when we work, but we'll just take that for granted for now. So we'll just kind of include like, so the reds and the red and the blue also kind of have infinity on there. But we're going to swap things around a little bit, change our cubics up. We're not just going to do the red lines as 1 cubic and the blue lines for 1 cubic. We're going to swap a couple things over. Okay, we're going to do a little swapping. Okay, we're going to swap. So here, notice, let's see, we're going to swap. So here, this blue should have really been red, right? And this red really should have been blue like it was up here, but we're going to swap them. We're going to swap them and then have a red cubic and a blue cubic again. And those are the two cubics that we're going to use that are made out of lines, and we're going to still keep the elliptic curve, which is a cubic itself. Okay. So, okay, so our list so C1 is now this new cubic where we swap things. And let's see kind of the points on C1 that intersect E are what they are. So we have A, B, this. Okay, so basically what are we swapping? So we still actually, the amazing thing about this is that we still have all the points from the red that we had before, because having this line as being red didn't give us any new points. But if we swap, we actually get new points. So we actually get the points that were at those intersections, which was when we were adding B and C. B plus C and its vertical partner is what we now append to the list C1 that we had before. The red list has now been expanded, and similarly the blue list will be expanded in the same way. we'll end up getting the we'll end up getting the result from A plus B right down here and its vertical partner. And that'll be added on. So our lists have just been expanded. And remember that we also have the point of infinity that's not on the list. Let's see, how many things in each list? 1, 2, 3, 4, 5, 6, 7, 8, and then the point of infinity is 9, which means that C1 is a cubic, intersects our elliptic curve in 9 places, and C2 also intersects it in 9 places. So both of them intersect the elliptic curve in 9 places. And in particular, how many places do they share themselves? Okay. All right. So C1 and C2, let's see. Well, if we look at these lists, right? Let's see. So they both have A, they both have B. Negative A plus B is in both. A plus B is in both. C, yes, is in both. And let's see, B plus C is in both. Negative B plus C is in both. I guess the only one that we're really wondering if is in both is this one and this one, because these are described in 2 different ways, but we want them to be the same point. They will be the same, but we want them to be the same, but we don't quite know that yet. That's what we're after and what we'll be looking to show. So right now we know that the cubic for C1, the cubic for C2, they share 7 of the same things in these lists, but they also share the point of infinity, which means that they both intersect in exactly 8 locations. So C1 and C2 intersect themselves in 8 locations. They intersect the elliptic curve, each one of them individually, in 9 locations. So they're actually, this is all set up for a theorem called the Cayley-Bacharach theorem, or however you pronounce it, which those conditions actually tell us that that C1 and C2 actually actually intersect themselves at the 9th at the other location as well. So we actually get that they're equal. So that comes from this result. And I mentioned a few thoughts about how you can think about maybe why that result is true. However, you can look that up, study it, or wait for later or never to learn how that actually that theorem actually works. But in general, you're kind of using an idea which is similar to the fact that if you have like a degree 3 polynomial, it has like 3 complex roots. But if it has 2 real roots, actually the third one is also real. And we're kind of going to be using that idea because really we were working with real things. However, using intersection ideas such as that, because really that's like intersecting a polynomial with the x-axis. If you pretended like the x-axis could have complex numbers, then you'd have an intersection like that, and there'd be 3 places of intersection, right? So, but using kind of an intersection type of theory, similar to that one, or rigorously proven statements through a proof, we can actually arrive at this theorem, which tells us that we have the associativity. Now that's intersection type proof to show us that associativity really does hold. And in the next little subsection, though, the reason why we went through this, or one reason why, is because it kind of opens our eyes to associativity a little bit, and some things that we can actually do with associativity in a geometric sense. And we'll wait for the next little video to discuss that. Thanks for watching.